the good news is this is probably the easiest section of the video series because we just finished a chapter and we're going to start a new chapter. It's always a little easier the first section, right? It's a new topic, there's not so many details. But on top of that, this one's short and you're preparing for the exam. I don't want to overload you with stuff anyway, so we'll have a little easier than usual Friday. The bad news is that the WebAssign is based on an earlier edition, I think, of the textbook. And the problems don't seem to have a whole lot to do with what's in the section anymore. That's very unfortunate. We need to update the department homework. I'll try and get you prepared for the homework, plus cover the section here. But it'll be quick, and I don't think you'll find it very hard or very long. Here's what we want to talk about is vector fields and line integrals. We'll start line integrals on Monday. A function that assigns to each point x, y in the plane is called, what should we call it? If you give it a point and you get out a vector, we'll call it a vector valued function, or the more common term is a vector field. The idea is like gravity. At each point there's a vector pointing you in the direction gravity is pulling, and it has a strength according to how strong gravity is. And so if at each point there's a vector, you can call it a vector field, like a force field in the case of gravity, right? Or you can have a flow field, right? You got a fluid flowing through, and at each point you have a position, and the water's flowing in a particular direction with a particular speed, you make a vector there for the velocity vector of the water, you have a vector field. Here's an example of sketching a vector field. The book has nice examples. This is the book's example, basically. If in the plane I take x over square root x squared plus y squared I plus y over square root x squared plus y squared j, can I sketch that vector field? And WebAssign, I'll just ask you to identify it since you can't sketch on there. And we'll put that on the plane, R2, take away the origin, right? Because since you can't divide by 0 there. What does the vector field look like? The idea is that in a sketch is you can't draw an infinite number of vectors, one at each point, so you draw some representatives. But what should they look like to show you what, get you a feel for what the flow field is here? Well, you notice that square root this squared plus this squared, if you take the length of that, is square root of x over square root x squared plus y squared squared plus y over square root x squared plus y squared squared is the square root of x squared plus y squared on top over x squared plus y squared on the bottom. It's 1, right? So these are unit vectors. You draw them all 1 unit long. Furthermore, you know their direction, right? It's the vector with components x and y multiplied by the same thing, 1 over square root x squared plus y squared. So they're always pointing away from the origin. They're in the direction x, y. If you're at the point 3, 1, the vector points in the direction 3, 1. It's but 1 unit long. So that's what you do. At each point here, you go straight away from the origin 1 unit. At this point here, you go straight away from the origin 1 unit. Right here, straight away from the origin 1 unit. So that's an easy way to draw that one. This is an example of a unit vector field, they call it, right? Also, an example of a radial vector field where the vector valued function depends only on r, not on theta. So it'll have a radial symmetry. Here's another vector field. This is an important one for another reason. Look at the vector f equals minus yi plus xj. Well, how can we sketch that? Again, we can look at the length. Square root this squared plus this squared, and I wrote this wrong. It should be minus, let me fix it. Minus y squared minus y squared plus x squared is square root x squared plus y squared is equal to the distance you are from the origin. So at each xy that you're at, the length of the vector there is going to be the same as the distance to the origin. Now, what direction does it point? Well, if you dot minus yx, here it is, minus yx, with the vector xy coming from the origin, it's minus xy plus xy is 0. So it's perpendicular to a vector coming from the origin, and its length is the distance to the origin. You can figure out how this looks. If I come out to this point here, I have to be perpendicular in that direction, right? A right angle, and I go the same distance. I take this distance, put it perpendicular to the origin. If I'm 1 unit from the origin, I go 1 unit perpendicular. If I'm 2 units from the origin, I go 2 units perpendicular. 3 units from the origin, I go 3 units perpendicular. And then it turns out they all go counterclockwise. To see that, you just already know they're circulating. they can't switch directions because these are continuous functions. If it suddenly switched directions, these wouldn't be continuous functions. So I have to circulate one way or the other. But now by drawing one of these, you'll see it circulates counterclockwise, and then you just draw them all counterclockwise, go out a distance from the origin, draw a vector that length perpendicular to the line you just draw. You can sketch this circulation here. Well, let's see what else we can do here. We've been looking at the gradient. We said how useful that is for finding the direction of steepest descent, for instance, or finding a vector perpendicular to a level curve. Those were nice applications, yet more applications are coming. You won't see them in this section. We'll just introduce some new ideas. Using this notation, the gradient vector is d dx, d dy, sometimes called del, upside down delta, with an arrow over the top to show it's a vector operator. If you give it any function we know, we get back the gradient vector, but also we're going to define these things. The divergence of a vector field, we used to just apply this to a function, will be del dot f. So we can dot this with a function, and then what we get is d dx times the first component of f, or operating the first component of f, plus d dy operating on the second component, is what the dot product means here, df1 dx plus df2 dy. Isn't that easy? Or in 3 dimensions, we can also do all these vector fields in 3 dimensions. Then f is, I guess I didn't write it here, f1 of xyz I plus f2 of xyz j plus f3 of xyz k. It'll have 3 components. You take df1 dx plus df2 dy plus df3 dz. It's very easy to do the divergence, right? Just partial with respect to x plus partial with respect to y in 2 dimensions, and one more just like that in 3 dimensions. The curl also, if we have we can take del cross f, and we'll call that the curl. This turns out to be the divergence useful in things like fluid flow, how much is going outward radially. This is like the second example, how much circulation is there. We can use the curl to measure that in some of the later sections coming up. We'll get to those. So let's see, just to do some calculations. These won't even be in the problem sets. Like I said, they move them around. So, but you'll get to them, I think, in 16.3 or something. Divergence of f for this vector field. xy first component, yz second component, y squared minus x cubed third component. What is this divergence? You just take d dx of this plus d dy of this plus d dz of this. Easy, right? d dx of xy is just y, right? d dy of yz is just z, because you're treating z as a constant, right? And d dz of something that has no z is 0, so you just get y plus z. The curl of f, you just put this determinant, ijk, the gradient operator, and the components of the vector field. And now you just compute, multiplying I is d dy of this minus d dz of this, right? Multiplying minus j, divide by this row and column is d dx of this minus d dz of this, and multiplying k is, divide by this row and column, d dx of this minus d dy of that. And you calculate all those, you get minus xi plus 3x squared j minus xk. Easy, it's just a little longer than this one. So divergence and curl are very easy to calculate. You just want to memorize these for now, and we'll do some homework shortly. Finally, there's some stuff that's on the WebAssign that's not in the section yet. I think it's 16.3 is coming up, if I remember right. A vector, I should have put a vector over the top. A vector field is conservative on an open region if for some function phi of xy defined on the region, f is the gradient of a function. Alright? Does that term conservative sound familiar? Think of conservative forces in physics. Right? Like gravity is conservative. Other things are conservative. The electric force between charged particles is conservative. And it's the same concept. The only thing is in physics they usually say force field is minus the gradient of the potential. So there's that minus difference, but it's completely analogous. So suppose f, we'll just do this in the plane again just for simplicity, but you can do it in 3 dimensions. Suppose F is a vector field 2x plus yi plus x squared plus 3y squared j. Right? Assigns to each point in the xy plane this vector. Find the potential for it. Most vector fields are not conservative. I mean, gravity is nice because it is. But most vectors, things like friction, are not conservative. What is the potential to go with this, given that it's conservative? You know, so I say find phi to show it's conservative. If I can find a phi it's conservative, that this is the gradient of it's conservative. If not, it's not conservative. Well, if this is really a gradient of something, then this must be d phi dx, and this must be d phi dy. So, if d phi dx equals 2x plus y, then, right, 2x plus y is the partial derivative of phi, then phi must be the partial integral of 2x plus y with respect to x. Similarly, if d phi dy is x plus 3y squared, partial with respect to y, then phi must be the partial integral with respect to y of this, right? Well, we take the partial integral of 2x plus y, and we integrate 2x, we get x squared, but we integrate y, treating y as a constant, we get xy. And then there's an arbitrary constant, but the constant can be any function of y, right? Because when you take the partial with respect to x, that'll be 0. So the arbitrary constant is any function of y whatsoever. Now, when we take this partial integral with respect to y, right, integral of x, treating x as a constant is xy, integral of 3y squared is y cubed because y is not treated as a constant, and then there's an arbitrary function of x when we're taking a partial with respect to y. So we know that phi, if this is really conservative, has to be equal to x squared plus xy plus some function of y alone, has to be equal to xy plus y cubed plus some function of x alone. Well, to make these match, it must be x squared as part of k of x, and y cubed is part of h of y. It must be that we have x squared plus xy plus y cubed, plus you can add an arbitrary constant on there and still make this work, but that's it. That's the most general function, such that d phi dx is this and d phi dy is that. So here is a potential for this vector field. You can take the partial derivatives again to check, you get these two things. Most people like to leave the c off and just put 0 here, right? Who wants to write an extra constant all the time? And then finally, one problem that I think is unfortunate because we don't use it for a while, and it's not in the section, so maybe you'll struggle with this one, but it's already in WebAssign, so I don't want to delete it. Phi is equal to 4 ln r. Suppose that is our potential, and r is the square root of x squared plus y squared, that's in polar coordinates. What is the gradient of phi in terms of ER? You can do unit vectors, not just I along the x-axis, j along the y-axis. You can do ER, a unit vector away from the origin, right? A radial unit vector, like in the first example. That's what this is. The unit vector away from 0, 0, ER. How can I write the gradient? Well, I just compute the gradient as d phi dxi plus d phi dyj, the vector partial derivatives of phi. Well, to compute d phi dx, where phi is a function of r, I use the chain rule. It's d phi r dx plus I plus d phi dr dy dyj. So this is partial with respect to x, this is partial with respect to y by the chain rule. Derivative 4 ln r with respect to r is 4 over r. And dr dx, where r is this, you can compute it. It's just x over square root x squared plus y squared. Derivative 4 ln r is 4 over r. Derivative y with respect to r, where r is this, is y over square root x squared plus y squared. So we get 4 over r times the vector x over r, right? This is x squared root x squared plus y squared is r, y over r. And now you notice something from the first example, x over r, y over r is a unit vector, e pointing away from the origin. This is ER. So the gradient is actually equal to 4 over r times ER, the unit vector away from the origin. Try that one for the homework. Go have a nice weekend.